So then welcome to the fourth lecture in the Introduction to Lattice Boltzmann methods in the winter term 2023-2024. So today we'll actually arrive at the Lattice Boltzmann equation. Today only in one dimension, but this is of course, the first step to actually understand what we are going to do in more than in 2 and in 3 dimensions. So we first continue a little bit with the Navier-Stokes equation. So with what we derived last time, where we arrived at the lattice Navier-Stokes, not Navier-Stokes, Navier-Stokes equation in the or the Navier-Stokes limit of the BGK equation. So this was last week's topic. What we arrived at was usually write Navier-Stokes equation like this. So this actually has a density. So in the Navier-Stokes equation, it is of course a mass density, because we had the particle density called rho. I'll now call the mass density rho with an asterisk down there. And this was the time derivative of u plus u into nabla u, and this this is equal to minus the gradient of something that is cs square rho asterisk plus tau cs square rho asterisk and the Laplace operator applied on u. So this is the Navier-Stokes equation. If we identify the speed of sound squared times the mass density, if we identify this with the pressure, and if we identify this here, all of this together as the viscosity. So the speed of sound actually is related to the temperature, so the speed of sound square, of course, to the molecular, say, the thermal energy in the system with the transfer factor K-Boltzmann, the Boltzmann constant, times the temperature, and will denote, as I said, this rho asterisk as the mass density, so this will be kilograms divided by cubic meters. So now recall again from last time, recall that tau was related to the Knudsen number times the Mach number, and obviously cs square is related to 1 over the Mach number square, such that this tau times cs squared that we have here in our viscosity term is then related to the Knudsen number divided by the Mach number, and this we define as a new number that you've probably heard about. This is the 1 over the Reynolds number. So for these dimensionless numbers, is of course always arbitrary how you define them, up or inverse or the other way around, and this turns out to be this way around. So this is the Reynolds number. You heard about the Reynolds number, right? Yeah. So the Reynolds number is given, depending on whether you write it with the kinematic or the dynamic viscosity. Now I'm going to write it with the kinematic viscosity, is the velocity scale times the length scale of the system divided by the kinematic viscosity. So the alternative, you could also write this is the velocity times the density here times divided by mu, because mu is the dynamic viscosity and this is rho asterisk times nu. So there's no difference between the two, but potentially you will see the later more in textbooks, because if you deal with the Navier-Stokes equation, they will usually use the dynamic viscosity and not the kinematic viscosity. Using the kinematic viscosity is more like a physicist's thing. Do you know reason why we prefer to work with the kinematic, with the dynamic rather than the kinematic viscosity in practice? So engineers. There is an advantage of this thing, especially in air. You know, it's called dynamic. So if the density changes, yeah, it's called dynamics because it looks like that it's changing. However, if the density changes, then the time in between collision also changes. And this is exactly inverse. So the dynamic viscosity is independent of the density because it is dependent on the density in two opposing ways, right? So it has the density inside, yeah, and it has the mean free time inside, and the two cancel each other out, such that the dynamic viscosity becomes independent of the density, while the kinematic viscosity is dependent on density. And this is why usually, if you ask about the viscosity, you ask about the dynamic viscosity. Yes, it's easier to deal with. Okay, now this was the Reynolds number. Yeah, okay, we have to get, in order to be complete, say this is U is the velocity scale. The velocity scale, L is the length scale. And nu is the kinematic viscosity. This is the one that we usually use here. So, and of course, as a reminder, the derivation that we had last week in lecture 3 was under a certain assumption. There's under the assumption that, yeah, it sounds a little bit crazy. Knudsen number must be larger than 0, otherwise we end up with the Euler equation. And Knudsen number square must go to 0, otherwise we are not getting anywhere. So Knudsen number is small, but finite. Yeah, so this is the case that gives us the Navier-Stokes equation. Knudsen number small but finite. Finite. So then there is something that kind of comes from engineering. Yeah, I have the observation that apparently, I don't know, my lecture my lecture seems to be difficult, so that people learning Lattice Boltzmann from the previous years, they look a lot in this book by Krüger in order to get their information from other places, and then they learn something about the Chapman-Engskog expansion, yeah, because this is very prominent in this field, and then you could be surprised that in this lecture we'll not use this kind of expansion. And in case you have already heard about this and wonder why we are not going to do this, and this is related to the fact that the Chapman-Engskog expansion is a valid analysis tool for the Boltzmann equation, where you want to get the large scale behavior of the Boltzmann, so the behavior on a larger scale. So there are atoms down there, yeah, that collide, and we want to come actually to a partial differential equation on a continuous limit, and for this we make our system larger and larger. Yeah, so this is how physicists analyze the Boltzmann equation. You make the system larger, yeah, and so you asymptotically end up on this differential equation, which are the Boltzmann, the Navier-Stokes equation and the Euler equation, for example. Now, that's completely valid from a physical point of view, but in engineering, we are looking at fixed size problems usually, right? So we have a certain problem, and this certain problem is usually described by a fixed Reynolds number, right? Yeah, your problem, your car, whatever you want to simulate is given by a fixed Reynolds number, and this is this has some consequences here. So you're not increasing the size of the system. Fixed Reynolds number means that Reynolds number, so Reynolds number was the Mach number, obviously the Mach number divided by the Knudsen number, and this is for any given problem, it's a constant. Otherwise you're comparing apples with watermelons, yeah? Things of different sizes, yeah? So, what does this mean? If this is constant, then obviously the Mach number scales the same as the Knudsen number. In this picture, which of course is not necessarily the case, because they are different things. One related to the speed of sound and one related to the distance of particles. And one thing that you have to be aware, that the Navier-Stokes equation is not really the truth, even though it appears a lot like it would be. There are some, so you could say it's already falsified, very obviously. Some observations contradict the Navier-Stokes equation. So very briefly, so my favorite is that according to the Navier-Stokes equation, two bodies that are immersed in any kind of a fluid, so for example air, will never touch. It is impossible for two bodies to touch. So what happens? If two bodies want to touch, if there's body 1 and there's a body 2, so if ever they want to touch, they have to move towards each other, right? So there would be a velocity u1, yeah, and the velocity u2, and one is going this way and one is going that way. And now there is fluid around these bodies, and the fluid directly on the surface of the body has the same velocity as the body itself, right? So it's taking everything with it. So the velocity close to the body, or the body surface, is the velocity of the body. Because there is no slip. So, and now when they get closer and closer to each other, this fluid in between has to be removed, and while it is being removed, the pressure will increase, and the increasing pressure will drive the bodies away from each other. Yeah? And the closer they get, the larger the pressure gets, and the larger the force gets to drive them apart. Right? And therefore they will never actually touch. Yeah? And then you can discuss with your mathematical friend whether this is actually the truth or not. So there is a reverse to this. What is actually the reverse to this? That two bodies that are in contact with each other can never be separated, right? Yeah, this is the inverse. Because you would need an infinite amount of force to drive them apart. The reason for this is that in the Navier-Stokes equation, the pressure comes in as a potential, and this potential has no bounds. It has no physical bound. It can go to minus infinity, and then the force will be minus infinity. Now, if you think about what pressure actually is, you should know that pressure cannot go to minus infinity, because there is, if everything is removed, if there is a vacuum, yeah, this is the minimum pressure that you could have, right? And so actually this force would be finite instead of infinite, as implied by the Navier-Stokes equation. So they would drive them apart. Now, is this true? I mean, today is Friday, so we can have a little bit a story. Yeah, there was a guy. I was in a commission that looked for a professor. So choosing a new professor, and for a fluid dynamics chair, and there was one guy actually applying there who was a mathematician and talked about this paradox that if you have a piece of paper lying on this table and you want to lift it, you need infinite force, according to the Navier-Stokes equation. And because he was a mathematician, he was actually insisting on that. And I mean, he noticed that this is a paradox, but for him the truth was the Navier-Stokes equation, and he more or less said that the nature is behaving badly, yeah, because it does not fulfill the Navier-Stokes equation. If you want to lift the paper, you need infinite force, whereas the force that you could maximally need to lift it would be the atmospheric pressure, yeah, which is like the weight of 10 meters per 10 meter water column. Yeah, so this would be the most force that you would need to lift it, unless the paper is glued to the table, right? So, but you know, for this mathematician, this was such a fundamental thing because it is written in the Navier-Stokes equation that the force must go to infinity, and so he cannot lift it. That even though experiments clearly contradicted this, he insisted on this, and of course he didn't get the job. But think about this: you go to you apply for a professorship, so the guy could. I mean, the guy was a scientist working on the Navier-Stokes, working in fluid dynamics, yeah, so not completely a nobody, and still insisting on something that is contradicts all the observation in physics just because it says the Navier-Stokes equation says so. Okay, funny. But yeah, so okay, one question: could these people be right? Could it be right that bodies are not touching? Are we sure that they can touch? Yeah, because what these guys will tell you usually is, well, there is a thin layer of air in between. And this could actually be true. Yeah? It can, and sometimes it probably is true because the air may stick chemically to the surface. So I give you, so my favorite example, counter example to this is if you observe a raindrop. The raindrop, here you can actually observe that the raindrop will finally touch the ocean. How do we know? We know because they two merge. If they could not touch, they wouldn't merge. And sometimes you can actually observe that merging them is kind of difficult because you can see raindrops bouncing off from a surface of water. Yeah, without merging. But they do it once, maybe twice, maybe 3 times, and then they merge, right? So finally they merge. So finally the Navier-Stokes equation is not true. So the Navier-Stokes equation would, for example, not permit the merging of a raindrop with the ocean. So this would look very funny. So we would have a lot of form, yeah, open form probably. By the way, how does open form, when you simulate a raindrop in open form, they will merge? Why so? Even though it's the Navier-Stokes equation. Because they have finite resolution. Yeah, they actually, in a sense, this is the same reason as in the you know, the funny thing is that the Boltzmann equation behaves a little bit like a discretized Navier-Stokes equation. Yeah, because at the end it is discrete, and if you discretize the Navier-Stokes equation, you artificially introduce, you know, this small length scale, which in physics is the mean free path, and now you have in a discretized Navier-Stokes equation you have the grid spacing, yeah, and if the things get close enough so that there is nothing that you cannot fit anything in between, though they merge, right? And this is the same reason. This is the same reason here, because if two bodies come close to each other, droplets, for example, so they would have a gap here. They would have a gap, and the gap, we call the length of the gap L. And then we have to compare this to the mean free path, lambda. And now the Knudsen number is lambda divided by L. So, and the Navier-Stokes equation is, of course, requires us, as we said, that the Newton's number is very small but non-zero, yeah? But in the gap, so in the gap, the Navier-Stokes equation, of course, also would not be valid unless, as we always say, that L must be very much larger than the mean free path. And when bodies get closer to each other, they will finally get closer to each other than the mean free path, and then the Navier-Stokes equation is over, and then other physics take over, or the real physics takes over. So finally, things merge or behave differently when the body comes closer than the mean free path. Yeah? So the mean free path for example, in air, we're talking about 60 nanometers, depending on the pressure, of course. So this is when the Navier-Stokes equation is at its end. And you've seen 60 nanometers is kind of a small length. Yeah? So you can use the Navier-Stokes equation a long way, but not to the way when actually bodies really get into contact. Then it's over. Okay, and therefore, yeah, you see the Navier-Stokes limit is still very useful. And this is why we will focus for the rest of this lecture series on the Navier-Stokes limit. The Navier-Stokes limit of the Boltzmann equation. So the Boltzmann equation is a 7-dimensional equation, yeah, where we have not only the time as variable, as independent variable, and the velocity as independent variable, the space as independent variable, but also the velocities as independent variable. Yeah? In the Navier-Stokes equation, velocity is a dependent variable. In the Boltzmann equations, it's an independent variable. So we have much larger phase space, and this implies that we have to invest much more work, money, whatever, memory, to solve the Boltzmann equation rather than the Navier-Stokes equation. But what we are now doing with the Lattice Boltzmann equation is we solve the Boltzmann equation in the Navier-Stokes limit. So all we get out of this is also a Navier-Stokes solver. Yeah, we are not going beyond that. We could go beyond that if we take more moments, but we are not trying to go beyond that. And because we are not trying to go beyond this, we can also simplify the Boltzmann equation so much that we are paying the same as if we would solve the Navier-Stokes equation in the first place. So then last time we derived the Navier-Stokes equation in terms of Boltzmann moments, of the moments of the Boltzmann equation, to actually see what we have to do to see the Navier-Stokes limit of the Boltzmann equation. So this was, of course, lecture 3. And there we got to this this moment representation. So we get the time derivative of this moment m100 is equal to dx m200 d equilibrium minus dy m11 equilibrium minus dz m101 equilibrium, and then took this together with tau, and there was an ominous factor 1/3 dxx m300 equilibrium. So all of these things here in equilibrium. So this is the Navier-Stokes equation in terms of Boltzmann moments. So what we observe here is the highest moments that appear are the third order moments. So these guys, and also these guys, third order. So these guys also appear only in their equilibrium, not in their non-equilibrium state. Yeah? And this is important because otherwise we had the closure problem. The non-equilibrium of this moment depends on the fourth order moments. Yeah? So we'll end up here in third order moments. Okay, now this means that if we want to solve the Boltzmann transport equation in the Navier-Stokes limit, all that we have to keep is moments up to order 3, not more. So an approximation of the Boltzmann transport equation retaining up to third order moments should be sufficient for solving the Navier-Stokes equation. Okay, now we know what we have to do. Yeah? We take the Boltzmann equation, approximate it until the third order moments, discretize this, and then we have a Navier-Stokes solver. Okay? So, and now we start this first in one dimension, and later we'll extend this, not today, but later we'll extend this to more than one dimension. So discrete velocity model in 1D. So the 1D case has the advantage that it is easy to draw it in form of a characteristic diagram. We'll also use the characteristic diagram when we are in more than one dimension, but then it does not fit on the, then we'll have to make an assumption because then it does not fit on the paper. So let's see what the characteristic diagram is. So the characteristic diagram uses two dimensions, namely the time dimension that we draw up here. This is the time dimension, and we have one space dimension. Sorry, what am I saying? This is the space dimension, and this is the time dimension. Okay. You know, I have 6 lectures this week. I'm getting a little bit a little bit tired. Sorry. So, okay, one space dimension and one time dimension. Yeah. So you see, this would be problematic if we had this in more spatial dimensions. So now we are going to discretize these things. So we have points here that are points in space and in time. Yeah. So we have a state that is in a certain place at a certain time. Yeah. So the field and so you see we have known states at different times and at discrete times and discrete space. So, and we call, and this is a regular, this is why it will be called a lattice, yeah? Because it's a regular arrangement of all of our information here. Yeah? So there's always the same distance, which we call delta t, the time step, and always the same distance in space, delta x, which is the grid spacing. And in this, we have particles that are moving around. Oh, no, not particles, populations that are moving around, and what they can do is, for example, they cannot move. Yeah? So if they not move, they will just stay in the same place and go from one time to the next time level, right? So then they could also move to the left, or they could move to the right. This is what they can do. And this can actually happen. This is the wrong one. So this can actually happen to all of them. So they all look the same. So from all these points, they could go to the left, they could stay where they are, or they could go to the right. So this is always something, I hope this doesn't make you fall asleep while I'm drawing this. So don't forget. Okay, so now they are all moving. These are the different states. So here again, so this is delta x, and this here is delta t, and now the velocity, this movement, yeah, from here to here, moving in space according to time, this is, of course, the velocity. Yeah? So we call this c. C is the one grid spacing divided by delta t, and we call this the lattice velocity. So this is the velocity that you need to have in order to move along in the lattice. And you could have this positive or negative, or it could also be zero, obviously. So one thing I have to announce, even though it's kind of annoying, that in the literature, because we are using computer, yeah, we assume that all the dimensions here are vanish, or that we write them down as dimensional in dimensionless form, so that very often we omit. Well, you've seen that there is omission of these guys, and this of course means that things that are apparently of different order could be added together in some equations, yeah, because we simply say, so there's a coordinate 1, 2, 3, yeah, and times that 1, 2, 3, yeah. So the correct way of thinking about this is a bit like we express everything in the lattice units, yeah, and just that whenever you talk about velocity is given in delta x by delta t, and because this is implicitly known, you don't write it there. Yeah, so you're never allowed to actually use velocity in meters per second in a Lattice Boltzmann method. Yeah, so this will completely crash your code. It's not possible. Yeah, because of the assumption that delta x and delta t is always equal to 1. So now in this diagram shows us the different stages in which our simulation takes place. There are basically two stages. One is the streaming. Streaming is the transport of particles. And then the streaming is here in between these dots. This is where the arrows are. And then comes a collision. This is where the dot is. Collision. And then there's streaming again. And then there is collision again. So the algorithm, what the algorithm does, it is streaming the particles from one node to another node, and then it's colliding the particles on the nodes. Yeah, and yeah. So our system here has now three velocities. So velocities we write with xi usually, xi. This is I times the lattice velocity, which is of course I delta x by delta t, and I is in -1, 0, 1. So these are the three velocities that we got. Okay, now the steps, streaming. So particles sorry for miswriting, particles move with their respective velocity, so which is IC is I delta x divided by t delta t, where I is an integer. So the populations, so the F is a population, they more or less, they hop, it's very important, from node to node on a regular grid. This is sometimes also called exact shift. Now this is something very special to the Lattice Boltzmann equation, because usually in numerical methods you would have to discretize the transport, yeah, and there you would need to you would usually have some sort of interpolation. Yeah, something is moving from here to here. Yeah, then you need to interpolate it and shift the interpolation function. Now, because we have here this exact shift, we are hopping from one place to another place. There is no need for interpolation. Everything here is exactly conserved, just not the location, and it's moving exactly with the prescribed speed. So when we have streamed, then we collide. So we have the collision, and this is particles interact with each other on the node, which means they only interact with other particles being on the same node. So on the nodes. So what is this kind of interaction? This is a rearrangement of the populations. Rearrangement of the populations under conservation laws, so we have to respect the conservation laws. Which means the conserved moments at this node stay the same, whereas the non-conserved moments change. So this is, streaming is pretty simple. What we have to do in collision, this we have to find out now. Okay, let's talk about moments of this thing. Moments. As I said before, this is what we are all dealing with here all the time. So MA, this is not the Mach number, it's M index A. Yeah, you remember from moments in 3 dimensions, there's M, A, B, C, but now we are in 1 dimension, so it's only 1 index. Yeah, MA, and so the moment here is the integral from -infinity to infinity over Fi. Now Fi, because there's a discrete number of populations in our distribution, and this now has to be multiplied with the distribution where they are actually located, and because they are located in one place in velocity space, namely at a certain velocity, we'll express this by the delta function. So are you all familiar with the delta function? And this times the kernel and C by the power of A, and only 1 dimensional. Are you all familiar with the delta function? Yeah, so delta function. Delta here means the Dirac delta, and the thing with the Dirac delta is defined by the outcome of the integral, so that this guy here times function g of xi dx will just give you g of ic. So this is the definition of a delta function. Now we have the delta function under the integral. Now we get something very, so this is now, you know, like, okay, so we would have here the Einstein summation. So for all different i's, we do this for all different i's. So we get here 3 times them. Yeah, so will turn out to be Fi. So all the Fi. Yeah. Okay, maybe I should, to be a little bit mathematically more correct, say, okay, forget about Einstein summation. All the populations that we have in our system, we sum them up, yeah. And what we come out with is I by the power. So we just the function that we use is xi by the power of A, yeah. So this will give us the E times C by the power of A, right? So this is the moment that's coming out. And because we have only 3 of them, we can actually write now all of them down. So for example, we start with M0. So then the sum over Fi, so to the power of 0 will be 1. All of them will be 1. So this is why it's just Fi. And so this is the 3 of them. This is F minus 1 plus F0 plus F1. And this minus 1, so this is the way we write this. This is the negative lattice direction. And this is called a Miller indice. Miller indices in one dimension don't make a lot of sense actually, but in more than one dimension, this is a common way to describe lattices. Has anybody of you heard something like crystallography? No. So if you talk, so in crystallography, of course, you have to deal with lattices, yeah, with the structure of how atoms are combined with each other, and in these lattices there are certain directions, and in the crystallographic world they describe these directions with these Miller indices where they use small integers for directions and write, when the direction is in the negative, they write the minus on top of them. Yeah? So this is the usual way in crystallography to write things down, and it's called Miller indices. And now, because we are using a lattice, here we adopt the same method. Okay, so it's just the sum, the zero order moment is just the sum of all of them. So the first order moment, now the first order moment is because it's I times c by the power of 1, yeah, so then if I is 0, so this drops out, so we don't get an F0, and otherwise we just get the I in front of this, and the I in front of minus 1 is of course minus 1, and here, and this all together with the lattice velocity c, which later we will say is delta x by delta t, which usually will skip out. So M2, what is M2? So A the power is 2. So what does this mean for the 0? 0 times c by the power of 0, by the power of 2 is 0. So minus 1 c by the power of 2 is 1. So f minus 1, and what is with 1? 1 is also 1, right? So, okay, c squared. M3. I by the power, so minus 1 by the power of 3 is minus 1, and 1 by the power of 3 is 1, and here comes the c. So now you see, this is going on like this. Yeah, obviously this will be this. Okay, so now this c is a constant which is actually 1, right? What we now observe is we do not get any more information out of this after this guy here, right? So because this guy is equal to that guy, and that guy is equal to that guy. Why is this so? Well, if we count, so there's 1, there's 2, there's 3. So we have 3 moments which are actually independent, which makes sense because we have only 3 populations that are independent. Yeah? So we have 3 discrete velocities, means 3 discrete, 3 independent moments. Of course, we have all the other moments too. They are just not independent. And because they are not independent, this means that there is something that we call alising or aliasing. So what pronunciation you prefer, alising or aliasing? What is the proper? Aliasing. Okay, so you prefer aliasing. I think both of them are in different parts of the world. Aliasing. So aliasing means that there are that one thing has several names, right? It has an alias. Yeah, so this is something that we know from Fourier transform, yeah, where if you don't sample fine enough, yeah, the same signal will show up in different frequencies. And this happens here too. Now, is this a problem? Yes, it's going to turn out kind of a problem. Because, especially here, for the Navier-Stokes equation, we need up to third order moments. Do we have up to third order moments? We have 3 moments. So this sounds good, right? So we have 3 moments. Do we have up to third order moments? No, because we start with 0, unfortunately, to count. So there's 1 missing. Yeah? So we would have M0, M1, and M2, and M3. This is what we need, what we usually would need. Okay, so we'll resolve this problem in a minute, or in a few minutes, and just remind us what these things are. M0, this is the mass. And the mass is, of course, conserved. What is M1? Yeah, so if this is the mass, then, and we did not normalize it, then it would be no momentum. Yeah, so it would be, if we divide by mass, usually it would be velocity. Say the moment is momentum. So, and this is something that, again, we conserve. See, talking about velocity is always difficult to talk. Velocity is conserved during a collision, but it's not globally conserved. The thing that is conserved is, of course, the momentum. Yeah? So we'll have to be a little bit careful with this. So what would M2 be, actually?
Energy.
It would be energy, right? So, and now we come a little bit into trouble, because, of course, energy, from physics, you would say it's conserved. But in the Navier-Stokes equation, and we only ask for the Navier-Stokes equation, the Navier-Stokes equation does not imply that energy is conserved. Yeah? So you can add an energy equation to the Navier-Stokes equation, but the Navier-Stokes equation in itself does not care about the conservation of energy. And if we say we just want to solve the Navier-Stokes equation, we do not conserve this guy here, because it's not conserved according to the Navier-Stokes equation. Because if we would conserve it, I mean, this is the thing, if we would conserve it, the Navier-Stokes equation would not be enough, and then the thing that we said, we are done with third order moments, is no longer correct. Yeah? If we want to conserve momentum on top of this, we will have at least fourth order moments together with it. So, one thing that we did is, last time, we assumed that the temperature was constant, which of course is also not true if energy would be conserved, right? Okay, let's try to rescue all of this, even though we are one moment short. Say we get to a discrete BGK equation. So, our discrete BGK equation. M0, so what do we need in a BGK equation? In a BGK equation, we need the equilibrium, right? So we'll relax to the distribution or the population to an equilibrium. So we need to know what is M0 equilibrium. And since this thing is conserved, yeah, it must be the same. So the equilibrium is the same as the population before the collision. Then what happens? Because the population before the collision relaxes towards the equilibrium, and if both have the same mass, the mass will stay the same, right? So this is why equilibrium needs to be the same as the incoming and moment, and the same is of course true for the momentum. So M1 equilibrium is M1, and this would be, yeah, say this would be rho, and this would be rho times u. Okay, so according to the derivation that we did like 2 lectures ago, the equilibrium for the second order moment was, again, we are not normalized, so we'll have rho in front of this. Rho speed of sound square plus u square. So this comes from the Boltzmann distribution. Yeah. So if you take the second moment of this will drop out. And if we go on and look at the equilibrium for the third order moment, then this is something we also derived last time. It was 3 u rho cs square plus u square. So, I mean, I said I derived this. So you derived this by taking these Boltzmann distribution, which looks like a Gaussian distribution, and take the integral at the third order moment of this, and this drops out. So, you know, I usually use this is not necessarily that easy. I use a computer algebra system. I mean, doing it by hand. So I use a computer algebra system, and this is coming out. Okay, so this is how we derived it. Yeah. Now we need. Okay, so this is something that we do not have control over, unfortunately, right? Because we have this moment aliasing. Aliasing. Now, we try to rescue this by doing some assumptions. What we see here is that there is a velocity square, and there is a velocity again here. Now we could say that we are satisfied with small velocities. Now assume we are satisfied with the small velocities. So velocity is small. Then the third order in velocity, that could be assumed to be 0, right? Sorry. So, and this would simplify this guy to 3u rho cs square. And now we have this problem, M3 equals to M1. So, okay, in principle, I should multiply here. If you like, you can write this, but we've already decided to leave this out. Yeah, but in principle, I mean, to be dimensional correct, we would have to multiply the c squared to it, but we have been assuming that this is 1. Yeah? So this is kind of our problem, and this is called this alising. This cs square, of course, again is in physics, it's related to Boltzmann T. So it is related to a certain temperature. And this temperature was not specified other than it is constant. Yeah? Now we can look, or you could probably already see what you should do for your velocity in order to rescue this model. How would you rescue that model? So we have T is a degree of freedom for us, yeah? So when T is a degree of freedom for us, then CS square is a degree of freedom for us. So what should we do with CS square such that the model is rescued? Really no idea? So the equilibrium of M3 should be 3U rho CS square. Yeah? However, unfortunately, it is U rho. But CS square is a degree of freedom. So what would you do with CS square in order to make 3 CS square equal to 1? Come on, guys.
Multiply and divide by 3.
Yeah, what would you divide by 3? Okay, so the CS square, you could simply say CS square is 1 over 3 C square, yeah? And because we are saying that this is equal to 1, we would just define this as 1 over 3, right? So because we say C is 1. So, and this means that the speed of sound, of course, would be 1 over 3, technically with a C behind this. And if you define the speed of sound like this, then your moment will have the right value, right? So that's all that we need to do. Okay, now we have our equilibrium. We have 3 moments, we have 3 equilibria. Now we want to express our equilibrium in terms of the populations. So populations from moments. So we see M0 is F minus 1 plus F0 plus F1. M1 is F1 minus F minus 1, and M2 is F1 plus F minus 1. Which means, so we can inverse all of this. F1 is M1 plus M2 half, F minus 1 is M2 minus M1 half, and F0 is M0 minus M2. And if we put the equilibrium into it, then we get M0 so because, oh yeah, the M0 equilibrium, this was rho, M1 equilibrium is rho U, and M2 equilibrium is rho 1/3. So I'm not writing the C now here, U square U. So, okay, then because I'm not writing the C, I'm going to be now very bad, because in physics, you always know you can only add things together which are of the same dimension, but now you have to remember that our velocity is a dimensionless velocity, yeah? So this is why now this is going to work. So if we solve this for F1, then we get rho 1/2 U plus 1/3 plus U square. F minus 1 equilibrium is rho 1/2 minus U plus 1/3 plus U square. and the F0 equilibrium is rho two-thirds minus u squared. I think I can draw this a little bit more beautiful. Two-thirds. So this is our equilibrium. Now we know the equilibria for all the populations, and now we can do our Lattice Boltzmann algorithm, yeah, by, of course, looking at what we are doing, the lattice Boltzmann, lattice BGK now, because we are using BGK equation. Okay, a little bit of theory still to get an understanding of what we are actually doing. So we said the algorithm goes in 2 steps. And let's write them down mathematically. So the stream would look like this. There's a population Fi at the position x plus I c delta t. So new position t plus delta t, new time, is equal to a post-collision. We indicate the post-collision with this asterisk. I at the current position at the current time, okay? This is what streaming does, yeah? It turns a post-collision distribution to a pre-collision distribution in the future at the neighbor. So what does collision? Collide is giving the post-collision state is equal to the pre-collision state plus a relaxation frequency. So we identified this as in comparison to the original BGK equation where we had 1 over tau, which was a time. So then the inverse is a frequency, right? And this we call omega. Omega Fi equilibrium x and t. It will become clear why I prefer to use a different letter here in a different way in a minute. Fi x and t. So this here is the collision operator. We'll call this up here. This is streaming, so it is S, and collision we call this C. Okay. So some nomenclature. This is post-collision. So this here is pre-collision. And this here, omega, is the collision frequency. Okay. Now what we are going to do is we are rewriting the equation S a little bit in order to make it more useful for analysis. S. So it has turned out that even though this is the original form of the Lattice Boltzmann equation, that this is not the most convenient form of the Lattice Boltzmann equation. And we can very simply make it much more convenient with a very simple step, namely by moving it 1/2 time step and 1/2 grid spacing. So in the characteristic diagram, this is more or less to say, so the distributions or the populations exist in between the collisions, not at the collisions. Yeah, so in between the collisions. So what does it mean? We go now from x plus I c delta t 1/2. So we move 1/2 grid spacing and in 1/2 time step. Okay? And here, so I bring this post-collision state on the other side. So now if this happens, I mean, this is in order to make this more symmetric. If I move only half, yeah, I mean, in one time step, I move full. So this means I have here, I'm getting this from the other direction. So I do half of the movement here and go half of the time step here, right? Yeah. So half time step previously goes to half time step next time. Yeah. So you see, this is the same thing, just shifted in time, and the post collision taken to the other side. And I'm also rewriting the collision step as post-collision state here and now minus pre-collision state here and now is equal to omega Fi equilibrium here and now minus here and now. So we do this in order to simplify our Taylor expansion that we are now going to use to see how this thing is actually behaving. So Taylor expansion S, so we can Taylor expand the streaming operator at the development point x and t. So what is going to happen? That is what we'll call the equation 4.1. So we said we put everything on one side. This is the entire thing must be zero, obviously. Yeah. So then we take the first order the first order term, so the term at the development point, turns out to be this guy here, which kind of looks familiar, yeah, if you see this. So I guess it's not the collision operator, but it's minus the collision operator, right? Yeah, so there's a minus in front of this. And then comes the two different parts. So we do a Taylor series expansion in two directions, namely in time and in space. So first thing I'm doing is I'm doing it in time. So we move delta t half, dt fi x t, and now what happens is, because there is a minus in here and there is a minus in front of this, we'll come up with fi asterisk x and t. So with plus instead of the minus, then we'll have I delta t c. So this is according to the direction. dx, the 1/2, because there's a 1/2 in here. dx fi xt, and because there's also minus in here, so again minus in here plus times the minus in front of this gives a plus again. And then there are these double terms. So I made a mistake here. Okay, let's try to correct this. So we have we get from the Taylor expansion, we get a factor 2, a factor 1/2 at the second stage, right? Times the 1/2 that we have here. So I guess, even though this is not written on my script here, this must be 1/4 dt t. Now we have what is it? We are in time. So we have this here squared. So there will be a plus here times the minus which turns out that we get the minus here again, x and t minus fi x star x and t. Similar for the square dxx fi xt. So the same will happen also when we expand this in space. And then we have the mixed term. This is I delta t square c half dx and t, and this will behave the same way, xt minus fi star x and t, because we get one minus from minus delta t and one minus from minus delta x. Yeah? So this is what comes out, and then we get O of the order delta t cube. Okay, so now we have a little bit of a problem when we want to compare this to the original Boltzmann equation, because the Boltzmann equation just has the distribution f and does not distinguish before or after collision, right? So now question is, how do we define the actual distribution? Should we take the distribution f or the distribution f star? Since this is difficult to decide, I suggest we try to make it symmetric, because doing things symmetric usually leads to second order accuracy, right? And therefore, I will define, so this is a little bit Martin Geyer style, a few other people do it the opposite way. I will define this f over bar as the average between the pre and the post collision. Okay? So then fi can also be written, I mean, if I just turn this around, as fi over bar minus fi star, or this could also be written as fi half plus fi bar minus fi star half. Okay? Looks a little strange. Why am I doing this? I'm doing it in order to get rid of it in the collision operator. Let's look at the collision operator. Fi star minus fi omega. So then it's fi equilibrium minus fi, right? So instead of writing minus fi, I'm now writing this thing here. This is fi minus fi star divided by 2 minus fi over bar. Okay, so the problem with this before was, or still is, that this is an implicit equation, yeah, because there is the fi is on both sides of the equation, yeah. But what we see is that they are in the same form here and here, so we can put this to the other side, and then we have fi star minus fi, 1 minus the other, minus the one from the right-hand side, minus omega 2. And this is now omega fi equilibrium minus fi bar. Now saying that this fi bar is the original f from the Boltzmann equation, now that this actually looks like the BGK operator, right? It looks like the BGK operator if we say that fi star minus fi is equal to 2 omega divided by omega minus 2, Fi equilibrium minus Fi bar, and this is what we call equation 4.2. So now, again, we look at our Taylor expansion, which was equation 4.1. So our Taylor expansion looked like this. Fi, and now let me simplify this a bit. So it was delta t. So now we are simplifying it according to, so here what we had is Fi plus Fi star, right? And now this can be written as twice. So there was a 1 over 2 here. This is why this is going to disappear. So this is simply the time derivative of the barred version of df, right? So this is nice because later in our equation we want to have the time derivative of the actual quantity from the Boltzmann equation, and we have decided that we write this with the overbar. Comes with plus dt ic dx fi overbar, because there was the same thing here, and then the rest goes like this: delta t squared divided by 4 dtt fi minus fi asterisk. So we'll identify that this is related to the collision operator, actually. I'll use this in a second. T ic square divided by 4 dxx fi minus fi star plus dt square half ic dxt fi minus fi star, and all of this is of the order of delta t, and not delta t, it's of the order of delta, the rest is of the order of delta t squared. So now we unfortunately still have these guys here that we would like to get rid of. And the way we are getting rid of these things is by recognizing that what is written here is also written on the other side, right? And this, what is written on the other side, all of this is multiplied with 1 delta t, right? So if I substitute the equation into itself, what happens? What will happen is I'm substituting this into this here, and this here is already delta t, so this delta t out of this will multiply with the delta t square here and go to delta t cube. And by going into delta t cube, it will end up actually in here, and all of these guys will disappear. Clear? Yeah? So this means that delta t squared dtt fi minus fi star is of the order of delta t cube. So it will disappear, and what we end up with is fi star minus fi is equal to 2 omega divided by omega minus 2 fi eq minus fi over bar is equal to delta t dt fi over bar plus delta t ic dx fi over bar plus O of delta t cube, which means we end up with the Boltzmann, the lattice Boltzmann, the simplified Boltzmann equation. So you get the time derivative of fi plus I C. So this is the kinetic. You can see this is the kinetic advection operator. X Fi is equal to 1 over delta t, 1 over omega minus 1/2 into Fi equilibrium minus Fi bar. So this is the BGK operator, and all of this goes now to, because we divide by delta t, we divide by delta t, so it's delta t squared, so it's second order accurate. So this is the BGK equation coming out of our model, with something interesting, namely that tau, we have to identify tau as being 1 over omega minus 1/2 delta t. So it's not just 1 over omega, but it's 1 over omega minus 1/2. And this guy here is called the Eon correction, because Eon, I believe it's pronounced, was the guy who first discovered this with a completely different kind of derivation. Okay, I just write down 2 more things. So we started 2 minutes late, so we'll end 2 minutes late. According to the stencil that we use here is looking like this, and we have a naming convention for the stencils that goes into DQQ, where this D, so this D is the number of dimensions, and this Q is the number of speeds, such that this lattice here will be called, so this model here will be called D1QQ3, and later we'll look at tensor product lattices that usually look like DQQ, so the one-dimensional Q by the power of D, and this is in 2D, yeah, where 3 by the power of 2 is 9, will end up at D2Q9, and in 3D we'll end up with D3Q27, and this is what we are going to use in the later lectures. So thank you I'm a little bit over time, but let me just stop this.